Hello everyone, this is Prabhu Chaudhary and today we are going to start our first module, which is simply we will use our cadence virtuoso for a simple NMOS. What we are aiming to do, the aim is to plot the following characteristic of MOSFET and identify the region of operations: IDS versus VGS, ID versus VDS. The tool and technology we are using in this is cadence virtuoso 180 nanometer, the GPDK 180, and the analysis is DC and parametric. The DC analysis and parametric we will done in this module. And the first one is the linear region. We all know that these two things, the linear region, saturation region, and the cutoff region. We are not including here the cutoff region. We will use only the linear region and saturation region. Let me try to explain what is the linear region. The linear region condition, we all know that VDS is less than equal to VGS minus VT. Okay, ID, what the ID in that is Kn dash W by L, VGS minus VT, VDS minus KD in VDS square by 2. So what is Kn dash? This is the process conductance parameter, which is equal to mu and COX. The saturation mode, VDS is greater than VGS minus VT, if the channel length modulation is considered in our NMOS or PMOS, then the ID is equal to Kn dash by 2 W by L VGS minus VT the whole square into 1 plus lambda VDS. This is channel length modulation constant, right? What we are going to see in our first module is we will plot the IDS versus VDS in this when VGS is changing. Okay, so or we can use the VGS and IDS, the IDS versus VGS when the channel is long channel or short channel. We will see the effect of the long channel and the short channel, right? So what we will do, first we have to make the directory mkdir analog. We all know that the cadence virtuoso we have to apply some, or we have to write some code to start our cadence virtuoso. CD analog CSH and the source cadence CSHRC and the virtuoso. Let me start. VIRTUOSO. Okay, so after 10 seconds or it will start, right? So cadence virtuoso is going to start, and this is opening. Wait a minute, right? Now it's ready. First we have to click on the new. New library. We have to define our library. Just use our directory, like we will use the analog 7 here, which is we will use our S2, right, attached to the previous library, and we will use S9, right? Just click on the apply. Okay, we have to attach to an existing technology. What is the existing technology we are using with the GPDK 180? You will see that this is GPDK 180, and just click on OK. Now the library is successful. S9 is successful. Now start. First click on the new and then the cell view. So the cell view, you can name it sine 11. Okay, the type is schematic. Here we will use the schematic. Okay, now the new window will be open. So this is our schematic editor. Here we will plot, here we will draw our NMOS or a PMOS, anything we want. First we have to draw our NMOS. So just press on I. This is a shortcut key. Just press I, the button I, and the library is what the library is. The library is gbdk 180. What is cell? Just click nmos. So here it is, nmos symbol is there. Okay, and then hide, or you can just click on enter. Okay, so here this nmos is there. So just click escape, and you can check the values, predefined values of this nmos in our cadence tool. Just click here and just press q. You will see that what the specification is given already to the nmos. We can change it, but now we are not going to change it, just for the sake of your, you can understand better when the simplicity of this project is there. So length is 180 nanometer, the total width is 2 micrometer, the finger width, all this is a standard. Just click on enter. Okay, so again we have to press I. We have to introduce our sources. So just click on analog lib, and just click VDC, right? VDC, wait a second, VDC, right? This is VDC and the symbol, and the is, just click enter. So just place it one VDC here, one VDC here. Right? Why we are using it? Because we have to plot between VGS and VDS with respect to I now. That's why this is for VGS and this is for VDS. That's why. Just press escape, and then again you have to click on I, and just what else we want? What is the main thing we want? The ground which we will connect with the source and the negative point of these two sources. So just press on GND. This is the library, is like analog lib. So GND, press on GND and then click enter. So one GND is here, the ground terminal is here. Press escape, and now we have to connect all these points so that we will establish our connection. Just press W. W is for wire. So here the wire is appearing. Now just click and then click. Just connect all these points. Okay. The negative terminal of this we connect with the ground. The negative terminal of this is also connected with the ground. The substrate also connected to the ground. Now we will check, is this plot or the schematic is okay or working properly or not. Then what we will do, just click on this check and save, the check and save terminal, and we will see here that the schematic check completed with no errors and the NMOS Psi 11 schematic is saved. Okay, so it means that the points and all the things are perfectly matched and connected properly. So now we can start our analyzation. So just press on launch, ADEL, right? So we have to do one thing before pressing it. We have to name these sources. Just name it. Just press on Q. Okay. The VDC voltage, you will, what was that? VDC, right? VDS, drain to source voltage, no? So VDS. Okay, what is this? Press Q. This is VGS, right? Okay, So just launch ADEL and press right click and copy from cell view. This is the VDS and VGS. Just take the value like 1.8 volt. You can use any value, but I am taking 1.8 volt both. Okay, so the values is 1.8 volt. Okay, so we have to run the DC analysis now. So just press on the DC. There are many types like transient, DC, AC, noise, everything, but we have to first use our DC. So DC analysis, then save DC operating point, design sweep variables, anything. The two basic VDS and VGS. Just click on VDS first. We will do this change after. Okay, sweep range. Just to take the value sweep range start from 0 to 1.8 volt. Automatic. So automatic, just press on linear. The step size is linear. You can take the value of 0.1 here. Okay, and then the step size is 0.1 on VDS. Stasis sweep, we don't take the stasis sweep. Okay, sweep variable is design variable VDS. Then press enter. So here is the DC. Type enable argument is that, right? So what next? Then we have to our output node what we want, like what we want the graph to be, the IDS versus VGS, IDS versus VDS. So try to put to be plotting setup. Where is this setup? Right, so from design we are select this from design. Okay, we will select it. For IDS we have to choose this node. This, the square, pink square is appeared, it means that it is selected. Yes, this is NMO. You can change the name. You can change the name to IDS. Enter. Okay, so this is our schematic properties, and we have to change one more thing, right? We are using the GPB 180, then we have to remove this. So only cadence foundry analog 180 nanometer model spectra GPD is applied here. Okay, now what are we getting? Let me plot. Okay, so here the plot, the graph appeared. What the graph is showing, IDS versus VDS. IDS versus VDS. Okay, 0 0. This is starting from 0 0. Okay, you can change the style also. The style is like solid, you will see clearly. You can change color also. You can change the color like green, right? Or if you want to know what the specific point, what is the value at the specific point, just click on M. Right, this point is M1, which is the voltage is 462.581 millivolt, and this is the current, this is 950.332 microampere. Or we can use one more thing, marker, create marker, vertical marker. Okay, just apply. Okay, so this vertical marker will tell you the value at the specific point at specific time. So this will show that 1.1339 milliampere, and this is the voltage is 1.01 volt. So this is all about the IDS versus VDS graph. Okay, now we can change it. Now we can change. How we can change it? Just click on IDC and change the variable name. The variable name, first we have to VGS and click VGS, okay, and then click enter and just press on run button. You will see the new plot. Here is the new plot. Here is the new plot. So this is IDS versus VGS. You can see clearly, or you can change the style to solid, and with the help of marker you can see what is the value at what point. 800.92 microampere at 1.41605 volt. Okay, so this is the IDS versus VGS graph, right? So let me try another graph. What is that? So just this is VGS. We are selecting VGS, no? So just press on tools, the parametric analysis. The parametric analysis in which we will start VDS. Okay, just click on VDS and from 0 to 1.8 auto. Don't take auto, this is linear. Just take the value like 100,000 for speed, but you can take simply 10. It will show you the result, and press on run. Then let's see what is the new graph will get. That is, what is this graph is showing? This is IDS versus VGS when this VDS is changing. VDS is changing from what to what? This is 0 to 1.8 and VDS is changing from 0 to 1.8, right? You can solidify all this thing as you know, all can be solidified. So this is the plot we are seeing in our books, in our copies, in our notebooks, but this is the actual with the implementation. So what next? Let me draw another thing, one more thing. Like try this. Just select VGS, or what we are selecting here, VGS, no, just select VDS and click on enter and then enter. Just go on tools, parametric analysis, just go on the parametric analysis. Here's the parametric analysis. This is the parametric analysis. We are using VGS, no, so just change this VGS, right? All the things are same, 0 to 1.8 and then enter and just click on run. Wait a second, 100% and will show you the result. Let me check. This is the plot. So this is the plot, very popular plot of this NMOS. We all know what is showing this IDS versus VDS when VGS is changing. From where to where the VGS is changing? The VGS is changing from 0 to 1.8 and you can change this, all the things to solidify. Just click here and click, right click, and the style is solid. So here the colors are also different, so it is easy to understand. So just check at 1.8 VGS the current value is 1.1692 milliampere and the value of the voltage VDS is what is 1.41605, right? So this is all the 4 graphs we are seeing here. All these things are done already. So this is what VGS versus IDS versus VGS, this is IDS versus VDS, and this is IDS versus VDS when VGS is changing. Okay, So one more graph is also there, we have shown that. So now, so this is all for the today's class. So we will come again with the next topic. We will show the NMOS or PMOS together. We can use the CMOS characteristic also. We can show what the CMOS characteristic, CMOS inverter's characteristic is, can be seen by this cadence virtuoso. So the main objective of this simple NMOS transistor application is, or why I am using this NMOS only, is I have to use these to familiar you with this cadence virtuoso tool. So this is all about this class. So thank you very much. Hope you like it. Just subscribe my channel. Thank you very much. Good day.